One really nice property of homogeneous linear equations is that if you know some solutions, you can easily build other solutions to the differential equation. So here's an example. We have this differential equation y double prime minus 5y prime plus 6y equals 0, and it has these two solutions, e to the 2x and e to the 3x. And let's try to find more solutions. So let's just check that these are solutions. Well, let's check the first one anyway. I'll let you check the second one. So we're going to need two derivatives of y sub 1. So the first derivative is 2e to the 2x, and then the second derivative is 4e to the 2x. Those factors of 2 are coming from the chain rule. So plugging everything into the differential equation, we get 4e to the 2x minus 5 times, and then plug in y prime, that's 2e to the 2x plus 6 times y itself, and that's e to the 2x. And this is supposed to be 0, and if you add all of these up, you do get 0. So good. This is a solution to the differential equation. The same sort of thing happens for y sub 2. But if you look at the work that we did when we checked that this was a solution, if we had some constant in front of this differential equation, none of this would change really, right? We'd have this constant would be here, it would be here, so it would be here, here, and here, and everything would still cancel and we'd get 0. So we started with one solution, and what we got was a bunch of other solutions, all constant multiples of that solutions. The same thing would happen for y2, of course. y2 is a solution, and so we get a bunch more solutions, constants times y2. But actually, this isn't all, because right, the algebra for demonstrating that y2 is a solution is exactly the same, and this equation is built out of just multiplication and addition. Right, and multiplication distributes over addition, so if you add these two solutions together, so we're going to make a new solution, I guess, by adding them together. So that's going to give us e to the 2x plus e to the 3x. All of the calculus and algebra we would do to check that these are individual solutions would just distribute and make this sum a solution. So let's do that just to check. So y prime is going to be 2e to the 2x plus 3e to the 3x. Y double prime is going to be 4e to the 2x plus 9e to the 3x. And then when we plug all of this into the differential equation, we get y double prime, which is 4e to the 2x plus 9e to the 3x minus 5 times y prime, which is 2e to the 2x plus 3e to the 3x plus 6 times y, and y is e to the 2x plus e to the 3x. And this is all supposed to be equal to 0. Now, here's where the distributing happens, right? We need to distribute these constants like that. So let's gather up all of the e to the 2x's. So we get 4e to the 2x, and then we get minus 10e to the 2x. That's from the second piece. Then from this third piece, we get plus 6e to the 2x. Look, these already add up to 0. Okay, now let's gather up all of the e to the 3x's. So we get 9e to the 3x from this first piece, and then minus 15e to the 3x from the second piece. And then from the third piece, we get plus 6e to the 3x, and those all add up to 0. So yeah, this whole thing adds up to 0. So this sum of solutions is a solution. And you know, these pieces that we got as we were checking our new solution, these are exactly the pieces that show up when you check that the individual solutions are solutions, right? If we compare this 4e to the 2x minus 10e to the 2x plus 6e to the 2x, that's what we had way up here, right? Same thing. So it seems like it's no coincidence that adding two solutions gave us another solution. That seems like the sort of thing we can check in general. So let's do this in general. Let's write a linear differential equation. And in general, we can write that like some linear differential operator L times applied to y is equal to 0. So this is a homogeneous differential equation. And suppose we have solutions y1 and y2. These aren't the same solutions as from before. These are just names for some functions that for some reason we know are solutions. So the question that we're asking here is, are these things solutions? If we multiply one of these by a constant, is it a solution? If we multiply the other one by a constant, is it a solution? And if we add them together, is it a solution? Well, let's check. So first let's check C1 times Y1. So remember, C1 is a constant. Now L is a differential operator, and derivatives commute with constant, multiplication by a constant. In other words, you can move multiplication by a constant outside of the differential operator. So that gives you C1 times L applied to y1. What is L applied to y1? Well, remember that y1 is a solution to the original differential equation. What does that mean? Well, that means that if you put y1 into the original differential equation, it works. So that means L applied to y1 is 0. So this is C1 times 0, and that's 0. And that means C1 times y1 is a solution to the differential equation. The same thing is going to happen with C2, y2, of course. You move the C2 outside the differential operator, and then L applied to y2 is 0 because y2 is a solution to the differential equation. So you get C2 times 0, that's 0, and so C2 times y2 is a solution to the differential equation. So finally, let's check the sum. So L applied to y1 plus y2. So one of the key things that we noticed about linear differential operators, like L here, is that they distribute over sums. So this gives us Ly1 plus Ly2, and of course Ly1 is 0, Ly2 is 0, and that's because y1 and y2 are solutions to the original differential equation, and so this whole thing is 0. So y1 plus y2 is a solution to the homogeneous differential equation. So if you start with two solutions to a homogeneous differential equation, there are lots of ways to get more solutions. And in fact, you can combine these. C1 y1 plus C2 y2 is also a solution to the homogeneous differential equation. So if you start with two solutions, or indeed any number of solutions, you can combine them in lots of ways to get more solutions. This is called the principle of superposition for homogeneous linear differential equations. If you start with two solutions, you can make any linear combination of them, that is, multiply them by constants and add them up, and you get another solution to the linear differential equation.